Hello students, welcome to the fourth lecture on particle physics. What we have seen in the third lecture that there are scores of particles which have been observed in the various experiments starting from electron, proton, neutron, muon, etc. etc. We discussed many particles yesterday as we had proton, neutron, cascade, lambda, sigma, etc. Now the question is, are all of them having the same nature or they are of different nature? And what we have discussed that they are of different nature. Today we are going to talk about the nature of these particles, as we have introduced fermions and bosons, and we have discussed that fermions are those particles which obey Fermi-Dirac statistics, having half integral multiple of h cross, they spin, and they obey Pauli's exclusion principle and are described by antisymmetric wave functions. Similarly, bosons are the particles which are described by Bose-Einstein statistics. They do not obey Pauli's exclusion principles. Their wave function is symmetric in nature, and their spins are integral multiple of h cross, like we have pion, rho meson, kaon, etc. The particles which have got spin either 0 h cross or 1 h cross, etc. We are going to talk about them. Let's start with fermions. Fermions are classified into two groups. One, what we call by the name leptons, and another we call by the names baryons. Leptons are those particles which do not participate in strong interaction, while they participate in electromagnetic and weak interaction processes, while baryons are the particles which participate in electromagnetic, weak, as well as in strong interactions. And therefore, what's the difference between leptons and baryons? That baryons also participate in strong interactions, while their spins and Pauli's exclusion principle and all that, they have the same. And then when we talk about the leptons, we have in the standard model of particle physics three sub-classification of these leptons that we will discuss in the class. Therefore, we have leptons, we have baryons. Now, baryons are composite particles. They have got a structure, they are made up of quarks. Similarly, we have bosons like pions, kaons, etc. They are also made up of quark-antiquark pair. And then baryons and mesons, these two particles which also participate in the strong interaction, together they are called hadrons. Therefore, if I write hadrons, that means I mean baryons as well as mesons. Though baryons have spins different from the spins of the mesons, baryons obey Pauli principle while mesons do not obey Pauli principle. But both of them also participate in strong interaction. Both of them are not elementary object. Both of them are made up of some elementary object. Baryons are made up of three quarks and mesons are made up of quark-antiquark pair. Together they are known as hadrons. Therefore, the important point is that hadrons are baryons plus mesons, while we have separate category for the leptons. Now, when we talk about leptons, now in the standard model of particle physics, they are classified into three different generations. First generation, second generation, and the third generation. This is known as the electron family. This is known as electron family. This is known as muon family, and this is known as tauon family. In electron family, we have electron type neutrino and electron. In the muon family, we have muon type neutrino and muon. And in the tauon family, we have tauon type neutrino and tauon. These all electron, muon, and tauon, they are negatively charged particles. Okay, and these neutrinos are neutral particle. Therefore, the tradition is that the highest charge state is written at the top. That is why we are writing here neutrinos, and the negatively charged particle we are writing at the bottom. And these are the three different generations. Generation 2 has nothing to do with generation 1. Generation 3 has nothing to do with generation 2 or generation 1. And that means they are independent families. And in the standard model of particle physics, we assign lepton numbers to them, and separate lepton number to the electron, separate lepton number to the muon, and the separate lepton number to the tauon. And traditionally, since if you recall, it was J.J. Thomson who discovered electron in 1898. Therefore, to us, electron was the first particle, and traditionally that is why we call electron to be a particle and positron to be an antiparticle. This has nothing to do with charge. This is just historically we kept electron, we call electron as a particle or proton as a particle. Therefore, when we will talk about the baryon number for the particles, we will assign baryon number +1 to the proton, neutron, etc., and -1 to the antiproton, antineutron, etc. While proton, remember, has got a positive charge and antiproton has a negative charge. Baryon number for the proton will be +1, while antiproton it will be -1. Here, whereas what we have, electron, a negatively charged particle, has a lepton number, electron-lepton number to be +1, and for positron, the electron-lepton number is -1. Therefore, we have similarly the doublets for the antiparticles. We have E plus nu E bar, mu plus nu mu bar, and tau plus nu tau bar. Therefore, we have first generation, second generation, and third generation. And in this family, we have two particles with electron-lepton number equal to +1, and two particles with electron-lepton number -1. Because for the antiparticles, we assign electron-lepton number to be -1. Similarly, muon-lepton number for these two guys, muon and muon type neutrino, they are +1, while for antiparticle mu plus and nu mu bar, this muon lepton number is -1. Now, similarly, we have for the tauon lepton number to be +1 for tau minus and nu tau, and tauon lepton number is -1, +1 for the particle, these two, and -1 for these two, tau plus and nu tau bar. And you see here E plus is at the top and nu E bar is at the bottom, because E plus charge is positive. Traditionally, we are writing it at the top, and it is neutral. Therefore, here this is neutral and this is negatively charged, and here this is positively charged and this is neutral. Therefore, we assign independent lepton number to the first generation particle to be +1 and antiparticle to be -1, and similarly for muon, the particles to be +1 and -1 to the antiparticles, and so on for the tauon. And if I ask you the question, what is electron-lepton number for the muon? The answer is simply 0. What is the tauon-lepton number for a nu mu type of particle, this type of particle? The answer is simply tauon-lepton number is 0. And this lepton number is conserved in standard model of particle physics. In the standard model of particle physics, independently we have the conservation of electron-lepton number, conservation of muon-lepton number, as well as conservation of tauon-lepton number. That means if we are seeing any violation of these lepton numbers, then that means that process will not be possible. For example, if I write something like E minus plus mu minus scattering, going to E minus plus mu minus in the final state. Now, if I assign electron-lepton number, then this will be +1 for this and +1 for that. Similarly, muon-lepton number, if I will assign, this will be +1 for this and +1 for that. And that means instead of this mu minus, I cannot write any other particle like tau minus. I cannot write sigma minus, because then we will have the violation of electron-lepton number or muon-lepton number, or similarly tauon-lepton number. And this we will discuss in the next slide. Therefore, to summarize what we have the three generation of leptons. As you can see, generation 1, generation 2 and generation 3. And in this generation we have nu E and E minus, nu mu, mu minus, nu tau, tau minus, and these are the masses of these particles. For example, we know that mass of the electron is around 0.5 MeV, mass of muon is 105.6 MeV, and mass of tauon is 1.7 Jeff approximately. Therefore, these are the masses of the particles, and electron, muon, neutrino, or electron or muon or tauon type neutrino, they have infinite lifetime, while a muon decays or a tauon decays. And what will be the lifetime of mu plus? Since mu plus is the antiparticle of mu minus, therefore in the standard model, the lifetime of particle is the same as that of the antiparticle. If mu minus is going to live for 2.197 microseconds, then that will be also the lifetime for a mu plus. And similarly, that will be true for a tau plus. Therefore, the masses of mu minus and mu plus will be exactly the same. Masses of tau minus and tau plus will be exactly the same. And similarly, that will be true for the lifetime of the particles. Now let us take a few examples to see that how we assign lepton numbers to the particles. See, this is the example which I have written: E minus plus E plus going to mu minus plus mu plus. I am assigning electron lepton number first. This is +1 for this and -1 for this, while for the right hand side they are 0. And you can see that sum of the lepton numbers in the initial state is 0, and the sum of the electron lepton number in the final state is 0. Then when I will assign muon lepton number, this will be 0 for electron and positron, and this will be -1 and +1 for mu minus and mu plus. And therefore this will turn out to be equal to 0, and we have this 0 in the initial state. Similarly, if I take the example of E minus plus E plus going to tau minus to tau plus, now here we will assign Le and L tau. Since there are no muons involved, therefore there is no need of muon lepton number, and this will be +1, -1, this will be 0, and here we will have 0, 0, +1 and -1. And if instead of tau plus I write mu plus, then for mu plus this is not a tauon, therefore the tauon lepton number will be 0, and you can see that we are violating tauon lepton number conservation. Or equivalently, we can say that if I write here L mu 0, 0, 0 and -1, we are violating muon lepton number also. And therefore this process is not observed in nature if we are talking about the conservation of lepton numbers in the standard model of particle physics. Similarly, if I talk about say I am taking the example of E plus E minus going to 2 photons, which is known by the name pair annihilation process, or the pair creation process is for photons giving rise to electron positron pairs in the final state. What we are going to write it as E plus E minus, going to two photons, giving rise to two photons in the final state. This is a pair creation process, and this Le is -1 and +1, while for them it's 0, while L mu, there are no muon, there are no tauon, therefore we are not going to assign them. And as you can see, we are conserving electron lepton number. But instead of that, if somebody asks me that, can I write instead of electron, can I take mu minus and in the initial state? The answer is no, not allowed in the standard model, because then this guy will not be there, and you won't, neither you will be conserving electron lepton number, nor you will be conserving the muon lepton number. Though you are conserving charge, the total charge is conserved, but you are not conserving electron and muon lepton number. Therefore, this process will not take place. Therefore, we have to be careful that in assigning the lepton number to the particles, we have to separately assign electron lepton number to the neutrino, electron as +1 to the anti-neutrino, and E plus to be -1 for muon type particles, or the second generation for nu mu and mu minus +1, and nu mu bar and mu plus as -1, and the total electron lepton number in the initial state, Le, I should write it as initial, must be equal to Le final, or L mu initial must be equal to L mu final, and similarly that would be true for the tauon. Therefore, we have to separately conserve electron lepton number, muon lepton number, and the tauon lepton number in any process. Now let us come first to discuss strange particles. What was observed and why strange particle means its behavior was different. Behavior of these particles were different from the normal particles which were observed at that point of time. The particles which had a certain lifetime, the others had a much longer lifetime. For example, a delta particle whose mass is 1232 MeV, its lifetime is 10 power minus 23 seconds. Now, if few particles were observed in this mass range, I will say, whose lifetime was much larger than 10 power minus 23 seconds. While the production time was of this order, the decay time was much larger than this, and that is why such type of particles were called strange particles. And in the third class of this particle physics lecture, we have already described how the lambda particle was found, and today we are going to discuss more about them. Therefore, in the December of 1947, Rochester and Butler published the cloud chamber photograph of cosmic ray particles entering from the upper left and striking the lead plate, giving rise to a neutral particle. And you see the track which are being shown here, this has got a V shape. Therefore, they observed certain particles which get, after the interaction of that, another particle gets formed, and that particle has a lifetime which decays into such a V-type track like pi plus, pi minus, or mu plus and neutrino. Therefore, this is the important point, that this is a nu mu, and this is a mu plus, this is a pi plus, and this is a pi minus. Therefore, what was observed? That charge in the final state is 0 here in this case, and that means the particle which was formed was a neutral particle, and here the charge was positive. That means, to conserve charge, the particle which was formed initially was having a positive charge. Now it was concluded that the neutral particle decays into two secondaries, pi plus and pi minus. The presence of neutral particle was ascertained by looking at the decay mode, which was forming an upside down, something like that, this upside down, or the here we are showing it like here, upside down image in the lower right of the cloud chamber. This particle which decays into pi plus pi minus was called as K0, and similarly we had the particle which was found to have 3 pions in the final state, pi plus, 2 pi plus and 1 pi minus. That means overall the charge of that particle which is decaying is positive. Therefore that is a positively charged particle, and that was called as K plus. Therefore these particles were seen to have a very long lifetime, and in comparison to the lifetime of the particles which were observed to have about the same mass, but they were there or being formed for a very short time and then they decay. But here it was found that their lifetimes are quite large. Some of them were found to have lifetime of 10 power minus 10 seconds. Sometime they were found to have lifetime of 10 power minus 12 seconds, or even 10 power minus 9 seconds. And that is why while the strong interaction time is of the order of 10 power minus 23 seconds. Therefore these lifetimes were quite larger than the lifetime those are involved in strong interaction processes, and therefore these particles were called, for their strange behavior, they were called as a strange particle. Another neutral particle was found by Anderson group in 1950, and particles were identified to decay to proton and a pi minus, and this particle was called as a lambda particle. A lambda is decaying into p plus pi minus and again forming a V shape for the proton and a pi minus, and the total charge, as you can see, the total charge is 0. Therefore again that particle is a neutral particle, and it was found that this particle has relatively longer lifetime. Therefore it was found that these particles are produced on a time scale of 10 power minus 23 seconds, where their lifetime are quite large, of the order of 10 power minus 10 seconds, of the order of 10 power minus 10 seconds. You may call it by nanoseconds or picoseconds. Just I am writing it as 10 power minus 10 seconds. Then Pius and others concluded that the production mechanism of these particles are entirely different from the decay ones. They argued that these particles are produced via strong interactions but decay through weak interaction processes. Moreover, Pius argued that such particles are produced in pairs, which is known today as associated particle production process. Therefore, they found that these strange particles are being produced in pairs, and both of them, those produced particles, they have a longer lifetime. We will look at the example of such type of particles. Therefore, I am giving you an example that in the interaction of a pi minus with a proton, what they found that two strange particles are being formed. One is K plus and another is sigma minus. And they assigned strange, since they called them to be strange particles, they introduced a strangeness quantum number to these particles, and for K plus they assigned a strangeness quantum number to be +1, and for sigma minus they assigned strangeness quantum number to be -1, such that the total strangeness in the strong interaction process is conserved, because pi minus and p, they are non-strange particle, while K plus and sigma minus, they are strange particles with opposite strangeness quantum number. Therefore, this strangeness quantum number, like Lepton number and Baryon number, this has also been put by scientists by hand to understand certain reactions. Therefore, they are not required by nature. By nature, what we require is the conservation of charge, conservation of linear momentum, conservation of angular momentum, and conservation of energy. These four are the demand of nature. That without conserving these four quantum numbers, you cannot have any process. But in the standard model, we have an additional three that is known by the name lepton number, baryon number, and the CPT, which we will discuss in the class. These should also be conserved. Therefore, there are 7 exact conservation laws, which in the standard model, they have to be conserved independently. And here, when we are taking the example of strange particles, then we are seeing that in a strong interaction process, the strangeness quantum number is conserved. And this is an important point, that here also the strangeness quantum number is +1, and for lambda 0 it is -1, and similarly for k0. Therefore, for k plus and k0, the strangeness quantum number, those were assigned, was +1, and for k minus and k0 bar, the strangeness quantum number was -1. Therefore, let's stop here, and then we will start discussing about the strange particles and the different processes in our next lecture.